So in this video, we're taking a look at the first derivative test that is going to help us find our local maxes and local mins. And you are welcome to look at the symbolic definition of the first derivative test in your book. I think it's actually going to make a lot more sense if we talk through what the first derivative test is saying visually, and then look at a couple of examples of how we apply the first derivative test to locate the local extrema. So let's imagine for just a second that we have a graph, and this graph is going to look kind of like a sea serpent or like a sine wave or something like that. It's going to start low and then curve gradually up into a hill, and then curve down into a valley, and then curve up again into a hill. That's what it's going to look like as we move from left to right along the graph. Okay, so there is the graph that we're dealing with. And just graphically, just from looking at this, we can see that we have two local extremum, right? We have this local max here at the peak of the hill. And we also have a local minimum at the bottom of the valley, right? So those are our extrema. We know what they are. But again, if I didn't have this graph, I want to think through how could I find these things using calculus and using derivatives, because we're talking about the first derivative test. How could I find these things by looking at the derivatives? Well, here's the interesting thing. First of all, we know that our maximum and minimum values, those are going to be, in this case, at critical values, because at a max or at a min, our derivative is equal to 0, right? Then we start looking at other interesting things about the derivatives on either side. When we look at a local maximum, for example, to the left of a local maximum, the derivative is increasing. To the right of a local maximum, the derivative is decreasing. So as we read from left to right along the graph, if the derivatives go from positive to negative, that defines a local maximum. Okay. Similarly, when we're looking at our local minimum here, to the left of the local minimum, we're kind of headed down that hill and into the valley. That's a negative sign for the derivative. To the right of the local minimum, when we're coming out of the bottom of the valley, we can see that the sign of the derivative would be positive. So if when I find my derivatives signs on either side of that minimum, and if it goes from minus to plus, if it goes from negative to positive, that's how a minimum occurs. Okay. So what the first derivative test has us look at is it has us find these critical numbers, then look at the signs of the derivative on either side of the critical numbers, and those patterns tell us what kind of extremum we're dealing with at that particular point. The other thing to be aware of, there are cases where you can have a critical value and there's no extremum. That is totally possible. I'll give you a visual example here. If instead of having a defined hill or valley, let's say that we had a function where we're increasing and then we flatten and then we increase some more. So neither of these points right here, kind of these points where they, what am I trying to say? Kind of those points that look sort of flattened a little bit on the graph. Those are not true maximums or minimums because they're not like a single specified point. It's still curving there, right? Curving, curving. And then in here in the middle, we're flat. So here, where we're flat, that's still going to be a critical value. If we were to find the derivative of this function, set it equal to 0, we would still find that we had a critical value there. But you'll notice if we look at the signs of the derivative to either side of that flat portion, to the left of that critical value, we're increasing. To the right of that critical value, we're still increasing, right? There was no change in sign, so there is no extremum there. There's no min, there's no max, okay? So this is the kind of stuff we're going to think about when we apply the first derivative test. So let us take a look at an example, okay? Let's look at, let's say we want to find the local extrema of, and let's say we have f of x equals x over x squared plus 1. Well, to find the local extrema, the first thing we need is we need the derivative of the function, right? So that we can use the first derivative test. So first thing we're going to do is find the derivative of f of x. This is a quotient, so we're going to have to use the quotient rule. Quotient rule says take the function that's on the bottom, multiply that by the derivative of the top, minus the function that's on the top of the fraction, times the derivative of the bottom function, whole thing divided by the bottom function or the denominator function squared. Okay. And then it's probably going to make our life easier if we simplify this a little bit. So thinking about this numerator, distributing this 1 here, that's just going to give me x squared plus 1. Then I have minus x times 2x is minus 2x squared. And then I have an x squared minus a 2x squared in the numerator. So when this is all simplified, we're looking at f prime of x is equal to 1 minus x squared over x squared plus 1 quantity squared. And I'm actually just going to leave it like that. Okay, you don't need to FOIL out the denominator. This is just fine. Okay, so we found the derivative. Next step in the first derivative test is to set that derivative equal to 0 and find out if there are any places where it does not exist. Because if we do that, that's going to tell us where our critical values are. So step 2 is to locate those critical values. You'll notice this doesn't have any places where the derivative is not going to exist. Major things that cause the derivative to not exist are things like dividing by 0 or taking the square root of a negative, things like that. Here, if I look at my denominator, this is actually never going to be 0, right? No matter what I put in for x, even if I put 0 in for x, right, I'd have 0 squared plus 1. Well, that's going to be 1 squared. My denominator is now 1. It's not 0. Even if I tried to put in a negative 1 to try and cancel out the positive 1, because I'm squaring the x value, negative 1 squared is going to be positive 1 plus 1 squared. Nope, still not 0. So this is actually defined everywhere. So we don't have to worry about places where f prime of x does not exist. But we do have to worry about places where f prime of x would be equal to 0, right? That's where we're going to find our critical values. So 0 is equal to 1 minus x squared over x squared plus 1 quantity squared. Well, since this is a fraction, the only way for this fraction to be equal to 0 is if the numerator is equal to 0. I don't have to think about the denominator at all. Okay? So in order for my numerator to be equal to 0, x has to be plus or minus 1. Right? Because it's 1 minus x squared. Okay, so we need x squared to be equal to 1. That happens when x is either positive or negative 1, right? Because if we take negative 1 and square it, it's positive 1. So those are our two critical values. Then we're going to make our number line, just like we did in the previous video, because we're going to divide our number line up into 3 sections, pick a test point from each section, and find out the sign of the first derivative there. Okay. So for this left-hand portion, to the left of negative 1, I'm going to pick negative 2 as my test point. Between negative 1 and 1, I'll pick 0. And to the right of positive 1, I'll pick 2. Okay, so these are our test points. And then we're just going to plug each of those into our first derivative. But again, we don't care about the value, we just care about the sign. So if I had, for example, f prime of negative 2, well, that's going to be 1 minus negative 2 squared over negative 2 squared plus 1 squared. And all I'm going to worry about here is the sign. Well, the sign of the numerator, when I square negative 2, that's going to be 2. Or sorry, it's going to be 4 and positive 4. 1 minus positive 4 is negative 3. So that numerator is going to be negative. Negative 2 squared in the denominator, going to be positive 4, plus 1, positive 5. Square it, 25. So that's a positive, and negative over positive is a negative. So the sign of our derivative in that first interval is negative. If I look at f prime of 0, 1 minus 0 squared in the numerator just gives us 1. 0 squared plus 1 squared in the denominator also gives us 1. That's positive. And then if I want to find f prime of 2, 1 minus 2 squared over 2 squared plus 1 squared. And you'll notice sign-wise, this is going to work out exactly the same to f prime of negative 2, right? It's going to be negative in the numerator, positive in the denominator. Negative over positive is negative. So now I have to think about these two critical values. Negative 1, positive 1. Is either of them a max? Is either of them a min? And if so, which one? Well, if the slope of my derivative to the left of negative 1 is negative, and the slope of my derivative to the right of negative 1 is positive, what does that tell me about negative 1? It's a minimum, right? If I'm going from negative to positive. Similarly, with the value of positive 1, the critical value there, to the left of positive 1, I had a positive derivative. To the right of negative, or positive 1, sorry, I had a negative derivative. What is that? That's a max. So in terms of this particular function, we have two local extrema. We have a local min at, whoops, let's try that again, at x equals -1, and we have a local max at x equals 1. That's how we use the first derivative test to find local extrema.